There's this interesting, despite the fact that f, the little f itself, can be a very non-linear dynamic, there is actually a simple linear structure which exists in symbol space. So for example, if you had two of these symbol sequences, and suppose we thought of this left shift operator as operating on them, so just shift everything to the left and remove the one on the left and so on. If you defined plus as just mod 1 addition, let's just say that again. If you took these symbols and treated them as zeros and ones, and then just thought of these zeros and ones as the binary expansion of some real number, and then added these together, let's say mod 1, so 0.101 plus 0.011 would be plus 0.10, and then just put that back into symbol space, so 010 plus 011 equals 101. Then basically the action of f, the shift sequence, is kind of linear on that thing. So f applied to SA, defining this addition of symbols by going into binary reals, add mod 1 and back again. Then f acting on SA plus SB is just f acting on SA plus f acting on SB. And a simple way of saying that is just this f, if it's a left shift, it's like doing a multiplication by 2 and then doing mod 1. So simple multiplication is distributed over addition. You have this kind of linear structure. So even though f itself, little f, is a highly non-linear operator in state space, this capital F does actually contain linear structure, which I think is rather interesting. Anyway, right. What's this got to do with quantum theory? So I just want to kind of now go to a rather different direction and just think about symbol sequences and how possibly you could ever get to the notion of a complex Hilbert space of a n-qubit vector, n-qubit state vector. 2 points I want to make about Hilbert spaces is that, you know, as people often say, Hilbert space is vast. So an n-qubit state vector has a 2 to the n dimensional Hilbert space. And the second thing is complex Hilbert spaces are complex. They have imaginary numbers. So how to sort of encode at least or incorporate these two kind of key ideas into this notion that we could possibly write a quantum state vector by a symbol sequence. So, again, I want to return to this idea of thinking about a symbol sequence. And again, if you like, you can have up oranges and down oranges. And I'm just going to define this symbol, which looks like a minus sign, as something which just transforms an up orange into a down orange. Sorry, that should have been a down orange into an up orange. Anyway, so it's just, it transforms one into the other. And so let me call it negation of the sequence will just be this operator applied to all elements. So in particular, the negation applied to the negation, so if you go from an up orange to a down orange, then minus brings it back to an up orange again. Minus equals original. Well, again, just not to bother with oranges all the way through, let me use zeros and ones, but just remember that I'm writing minus 0 equals 1, but this minus sign is just inverting the symbol. Now, with the simplest thing is just to think, oh yeah, I should say I'm considering a symbol sequence which has 2 to the n binary symbols. So n is going to be some very large number, but to start with, let's just consider n equals 1. 2 symbols. And I'll define this I operator as this. So you take the second element and move it to the front and apply the minus operator. Then you can very quickly see if you apply I again to this, you take that second one, move it to the front with a minus, you just get minus A1 minus A2, and that was minus of S. So I've got an operator which is a bit like a square root, well it is a square root of minus 1, applying to S. If you want to, you can write this as a kind of as a kind of like a little matrix operation, thinking this as a row vector, where this matrix will be a 2 by 2 matrix, a bit like Maurice's, your bio matrix, 1 minus 1. Okay. If we continued a little bit further with n equals 2, so now we have 4 elements, 2 to the power 2. It's now very straightforward to define square roots of minus 1, which have some interrelated structure between them. So, again, this is just a permutation sort of operation. Take the second element, move it to the front, put a minus sign in. Take the fourth element, move it to where the third one was, but don't have the minus sign. So if you do that twice, you'll see that e1 squared gives you minus 1. And similarly, this and this. But if you actually compound e1 and e2 together, and e2 and e3 and so on, you'll find that these actually satisfy quaternionic multiplication. So by these sort of sets of permutations, you've got something entirely equivalent to quaternionic multiplication. Now, again, that's not a total mystery if you use this matrix notation. And these E's now are, well, they're basically 4 by 4 matrices. So I'm using the fact that I is a 2 by 2 matrix, and this 1 is a 2 by 2 identity matrix. And now these matrices, which, if you like, affect the permutations, can be written in this way. And these, in fact, are nothing other than essentially the Pauli spin matrices. But remember, I is a 2 by 2 permutation matrix. And again, we have this the Weil matrix now again, but with this as a 2 by 2 unit matrix. Well, we can continue this kind of trick, if you like, by invoking a kind of self-similarity principle. So if we go to n equals 3 now, so 2 to the 3 is 8, we can now define. So we had with n equals 1 we had one single square root, with n equals 2 we had the 3 quaternion square roots of minus 1. With n equals 3 we get 7 square roots of minus 1. And what I've done is basically to take, that structure, but now to substitute in, instead of the I, to substitute in E1. So there's a kind of self-similarity here. And E2 and E3. So on this top row, you've got that I minus I matrix, but now instead of I, I've got the E1, the 4 by 4. So I've got 3 of these. There's my new Weil symplectic matrix, and then that's the other term in the quaternionic thing, but instead of I, I've got E1, E2, and E3. So I've now got 7 square roots of minus 1. With the identity matrix, I've got sort of 8 altogether, which sounds a bit like octonions. Now, I didn't think this had anything to do with octonions, but I remember last year, Freddie, you mentioned this thing called a smash product, which might transform these into octonions. And this is something I confess, followed through, so I'd like to talk with you a bit about this again, to see if we can make some linkage there, because that would be, I think, quite interesting. But anyway, there's nothing now stopping you just carrying on for arbitrary n. And for arbitrary n, the essential ingredient is to use self-similarity. And again, this is the whole kind of fractal stuff coming in to some extent, where you can define 2 to the n minus 1 square roots of minus 1. And there are a number of these quaternionic triples embedded within them. In particular, if you take these 2 to the n minus 1 square roots of minus 1 and consider the identity as well, and apply them, say, to just sets of zeros, you'll get sequences, 2 to the n sequences. And the correlation, they're pairwise orthogonal, so the correlation between any two members of this sequence will be 0. And so I'm calling them an orthogonal set. They're orthonormal in a sense, but perhaps won't. All of these will have equal numbers of zeros and ones, so they in some sense have if you define a norm in terms of the numbers of ones in the sequence, then all of these have the same number of ones. But they're all